Welcome back. Today we're going to continue our exploration of 3.7 growth rate interpretive functions with an explanation of some of the independent practice. In class, we already discussed the Australia problem here using this spreadsheet that's attached to the assignment. Right now, what we're going to do is we're now going to look at this problem 2, where we study comparing linear and exponential growth, the different possibilities for Jane's 2 job offers. In order to explore this, please open up the spreadsheet and click on problem 2. After college, Jane has 2 job offers to consider. Job A is compensated at $100,000 a year, but with no hope for ever having an increase in pay. Jane knows that a few of her peers are getting that offer right out of college. Job B is for a social media startup, which guarantees a mere $10,000 a year. The founder is sure the concept of the company will be the next big thing in social networking and promises a pay increase of 25 at the beginning of each new year. So if we set up our table, we have year, job A, job B. So in job A, no matter what, Jane is going to get $100,000 every single year. In job B, she's going to start out with $10,000, and then she is going to get 25% more each of the following years. There are a couple different ways we could represent that. We could either calculate it by hand, adding 25% each time, or if we want to make this a little quicker, we can use the following model, where we say starting with 10,000 times a growth rate of however much you have, plus 25%, raised to the number of years that she's been in the job. So in year 1, she's actually been in the job no time. So that's year minus 1. So she gets $10,000. We currently have an error, which means there's something we mistype in the equation. Let's see if we can find that. The error is that comma that we put into 10,000. The comma has significance in spreadsheets, so when you enter numbers, we enter them without commas. Now, hitting enter, it's 10,000. We pull this down, and in year 5, she's only making $24,000, which is much less than the $100,000. In fact, something to consider is if we go with the current minimum wage of $15 an hour, which is currently being debated in a lot of policy circles, for $10,000, let's see, $10,000 divided by 15, she should only do about 66 hours of work, so hours of labor. And that means weekly, assuming that she takes 2 weeks off every year. This divided by 50. This means this could be a kind of a side job for her where she does about $12, $13, $15 hours of work after her main job. So if she wanted to, she could take the $100,000 job and then do this on the side. Taking a look at this, now we're going to take a look at a different type of problem where again we have a linear growth and an exponential growth. And this second problem is in problem 3. The population of the town in 2017 was 15,000 people. Remember, people grow in exponentials, either exponential growth or exponential decay. The town has gotten its fresh water supply from a nearby lake and river system with the capacity to provide water for up to 30,000 people. So there's its hard limit. Due to the proximity to a big city and a freeway, hence jobs, the town's population has begun to grow more quickly than in the past. The table below shows the population count for each year from 2007 to 2012. So when we're deciding on a model that we're going to create for this, since the problem says, write a function that closely matches the data points for the x values, we want to get a picture of what this data looks like. The best way to get a picture is by making a graph. So we're going to insert a chart, waiting for the command system to come up, and we're going to actually pick a line chart or a scatter point chart, where we're going to choose. We're going to talk about how to then interpret this data in the next video. I'll see you there.